Think on a bam bam. Look what's on Jamaican. Little different style, different fashion. You know?
We'll start this video by recalling something that we proved last time, proposition 11 in section 8.3. That is, in a PID, a non-zero element is prime if and only if it is irreducible. And we're going to take this result and adapt it to apply to a UFD instead of a PID. And this is significant because, as we just said with the examples, every PID is a UFD, but not every UFD is a PID. So proving the analogous statement for UFDs includes more examples than PIDs. All right, so what are we going to prove? Let R be a UFD. A non-zero element of R is prime if and only if it's irreducible. And last time, we also proved that in an integral domain, prime elements are always irreducible. Right? So what do we have to do? This if and only one direction has any content to it that we use. Suppose we have P and R and irreducible elements, and now we want to show that it's actually a prime element, that if you're irreducible, you're automatically also prime in a UFD. All right, so we know we have these unique factorizations in a UFD, but what do they get us? Like, how do we use them for anything? And I like this argument because it's a good example of how to use the unique factorization to prove something. So, OK, so we have to show that P is prime. And let's do this by saying, all right, so P divides A times B for some A and B in R. And we want to show that either P divides A or P divides B. And OK, so what does it mean for P to divide A times B? That means A times B is equal to P times something for some C in R. And now, since R is a UFD, we can factor A and B into products of irreducibles. So this is the thing that is making this argument work. We write A equals alpha 1 up through alpha n, finite product of irreducible elements. B equals beta 1 up through beta m. And now, what is the factorization of A times B? It's alpha 1 up through alpha n times beta 1 up through beta m. But this is also equal to P times C. And we know P is irreducible. And now, since factorizations in a UFD are unique up to associates, that means we can factor C into a finite product of irreducible elements. And then there's going to be some way to rearrange the irreducibles over here so that the first one is associate to the first one, the second one is associate to the second one, third one to the third one in this other factorization into n plus m irreducibles here. So OK, after all that rearranging, P is going to occur in this list of finite irreducibles in the factorization of P times C. So that means that P must be associate to either alpha 1 or alpha 2 or alpha 3 or one of these alphas, or beta 1 or beta 2 or beta whatever up to beta m. So there has to be some irreducible on this list that P is associate to. OK, so that's the big thing that these unique factorizations are getting us. We have P times C equals A times B. We can factor A, factor B. We get this list of irreducibles. And we know that P has to occur somewhere in that list. It doesn't literally have to occur in that list. You might have a unit times C. But there's something in that list that's associate to P. OK, so for the purposes of making this argument readable, P is associate to some alpha I or some beta j. Let's say it's associate to some alpha I. If it were actually associate to some beta j and not some alpha I, let's just switch the names of A and B everywhere. Everywhere you see an A, just put in a B. And that'll just switch all the alphas and all the betas. So from now on, for the rest of this argument, let's suppose that P is associate to some alpha I. And if it's beta j, we're just going to switch A and B everywhere. And the proof will go exactly the same way. OK, so I'll pause and erase. And then I'll show you, once you know that P is associate to some alpha I, how to use that to see that P divides A. So we really, really are almost done with this argument. We know that P is associate to some alpha I. So we can rearrange the factors in this list and take that alpha I and write it first, that alpha I is u times p, some unit times p. And then we have all these other, then it would be that alpha I goes first. Then we have alpha 1, alpha 2, up to alpha I minus 1, alpha I plus 1, up to alpha n. But the upshot of it is we can write A as u times p. This is whatever that alpha I that p is associate to is. And then p2, p3 up to pn, where these pi's, these other p's, are irreducible elements. Like, we put alpha I first, then maybe p2 equals alpha 1, p3 equals alpha 2. These are just going to be the rest of the alphas in some order. OK, so let me just point something out, that it's possible that A is equal to just alpha 1, right? And then, OK, so p is associate to alpha 1. And this p2 up through pn, there are none of those. So that would just be A equals u times p. And that's fine. That's not an actual issue. But what does this mean? OK, so now clearly A is equal to p times something. So p divides A. All right, so that's the end of the proof. The thing that was helpful here is p divides AB means AB equals p times c. And you just factor everything in sight. And this is something you can do in a UFD that gives you information about irreducibles and primes. All right, so now I'm going to pause and erase, and I'll prove something for you about how to take greatest common divisors in a UFD. Let's talk about GCDs in UFDs by first talking about how greatest common divisors work in Z. So we talked all about Euclidean domains and explained how you could use the Euclidean algorithm, this repeated division algorithm, to find GCDs in Z. But if you start with two integers that are already factored into products of primes, you can compute GCDs much more easily. So it's not at all clear how you're supposed to just start with an integer and factor it into a product of primes. That's supposed to be like a harder problem than applying the Euclidean algorithm. But if you happen to start with two integers that are written as products of primes, let's say n equals p1 to the e1 up to pn to the en, where these p1 up through pn are distinct primes, and e1 up through en are non-negative numbers. So some of these can be 0. And m is equal to p1 to the f1 times pn to the fn. So it's the same set of primes, but now the exponents can be different, where these exponents, again, are non-negative. So it's like not necessarily true that p1 divides each of n and m. Maybe it divides one or the other. Well, then what is the greatest common divisor of n and m? Well, you could say, what is the biggest power of p1 that divides both n and m? And what is the biggest power of p2 that divides both n and m? And so on. And you'll see that the GCD is p1 to the minimum of e1 and f1 times p2 to the minimum of e2 and f2 times pn to the minimum of en and fn. So if you start with two integers that are factored, it's easy to compute GCDs. And proposition 13 in section 8.3 says that pretty much the same thing is true in a general unique factorization domain. That if A and B are non-zero elements of a UFD R, let's suppose that you can write A as u times p1 to the e1 up to pn to the en, and B is v times p1 to the f1 times pn to the fn, where u and v are units, p1 up through pn are distinct, I'll say primes for like parallelism here, but in a UFD, we now know that primes and irreducibles are the same thing. So distinct primes in R. And each of these exponents, ei and fi, these are all non-negative integers. Well, then D, you can set equal to p1 to the minimum of e1 and f1 times p2 to the minimum e2, f2 times pn to the minimum en, fn, where, OK, in this special case where all of these exponents, all the ei's and all the fi's are 0, we just set d equals 1. This D is a greatest common divisor of A and B. OK, how do you prove something is a greatest common divisor? Two steps. First, you prove it's a common divisor. And that part is clear. So why does D divide A? Well, the set of irreducible factors that could possibly occur in a factorization of A into a finite product of irreducibles, it's just P1 E1 times up to Pn En times. I say that could possibly occur because maybe E1 is 0 and P1 occurs no times. But the set of irreducible factors that occur, it's just P1 some number of times up to Pn some number of times. And D has that same possible set of irreducible factors. And the exponent of P1 in D is less than or equal to the exponent of P1 in E. Like P1 to the minimum of E1 F1 divides P1 to the E1. Either these are the same, or the minimum is P1 to the F1, and it's less than P1 to the E1. OK, so D divides A, since all the exponents corresponding to these irreducibles, P1 up through Pn, are at most the corresponding exponents for A. So if you just look at what these exponents are, it's clear that D divides A, that A is equal to D times something. And for exactly the same reason, D also divides B. Right? So this D divides B because all the exponents are less. So, OK, so what does that mean? D is a common divisor of A and B. So now we just have to show that D is the greatest common divisor. So what does that mean? If we have some C in the ring that divides A and divides B, we want to show that C divides D also. And what is the tool that we have at our disposal? Well, we have factored D into a product of irreducibles, and also the same for A and B. So let's do that to C, and then let's see what we can say. So I'll pause and erase and show you how to use a factorization of C to prove that, in fact, this D is the greatest common divisor, or sorry, A greatest common divisor. Let's finish this proof that D is the greatest A greatest common divisor of A and B by saying that if we have some common divisor C of A and B, then C also divides D. All right, so let's write C as a finite product of irreducible elements. So C equals Q1 G1, Q1 to the G1 times Q2 to the G2 times Qm to the Gm. Let's say that this is the prime factorization of C. So what does that mean? So Q1 up through Qm are distinct prime elements, and each Gi is greater than or equal to 1. All right, so since Qi divides C, and how do I want to say this? And C divides A and B, each Qi divides A and B. Okay? So as in the previous proof, when we were showing that in a UFD, irreducible implies prime, when you write out this prime factorization, Qi must be associate to some Pj, that set of irreducibles, distinct irreducibles, that occurs in the prime factorization of A. OK, so the same thing. This is true for each one. Q1 is associate to some Pj, Q2 is associate to some Pj, and these are all distinct, right? Distinct irreducibles. So up to associates, we have this set of, I guess I want to say more than these being distinct primes. I want them to be distinct primes where none of them are associate to each other. So it's not just like one is the negative of the other. So like pairwise, these are not associates. So Q1 is associate to some Pj in the list P1 up through Pn, and Q2 is associate to some other Pi, and those two things are not associate to each other, so they're not associate to the same one of these distinct these P's. So up to associates, Q1 up through Qm is contained in this set from P1 up through Pn. So one thing that says is that m is less than or equal to n, that the set of like distinct up to associates primes that occur in this prime factorization of C is contained in the set of distinct primes up to associates in the prime factorization of A. All right. So by rearranging the factors, by changing around the labels, which one is Q1, which one is Q2, we can suppose that Q1, or doing the same thing also, we're free to do the same thing over on the side with the P's as well. So let's just suppose that Q1 is associate to P1. You can think about how you would need to change the details if Q1 was associate to P2 instead, but okay, this is just labels and we're free to rearrange. So let's suppose that Q1 is associate to P1. That means Q1 is some unit W times P1. Then, okay, so C divides A. That means that A is equal to C times something. So here's C. It's Q1 times Q1 to the G1 minus 1 times Q2 to the G2 times QM to the GM times something, X in the ring, is equal to A. And what is A? A is equal to P1 times U times P1 to the E1 minus 1, P2 to the E2, Pn to the En. So I've just taken one of the P1s and like pulled it out to the front. All right, so now Q1 is equal to W times P1. And since R is an integral domain, we can cancel those P1s on each side. So what are we left with? W times Q1 to the G1 minus 1, Q2 to the G2 times equals, oh, sorry, this is C. I still have this X over here. So whatever this is, times this A, but with one fewer P1 in it. So U times P1 to the E1 minus 1 times P2 to the E2 times Pn to the En. So what are we seeing? Q1 is associate to some P1, and now you can cancel a factor of P1 on both sides of this equation. So you continue on in this way, and every time the exponent of Q1 is positive, you can cancel out. You have to have a P1 over on this side, and you can now cancel out that P1 from both sides here. So you can only do this as many times as you can lower this exponent of G1. You can only do it G1 times. And you can only do it over here E1 times. So what that's showing is that G1 is less than or equal to E1. And OK, now you just do the exact same thing, but instead of with Q1, with Q2, which after rearranging in the appropriate way, you can say that Q2 is associate to P2 or whatever. And you see that GI is less than or equal to EI for all I. So what are we seeing? Same idea. After rearranging appropriately, GI is less than or equal to FI for all I. So the exponents that are occurring in this C for the corresponding irreducible distinct up to associate irreducible primes here are at most EI and FI. So GI is at most the minimum of EI and FI for all I. What does that mean? That means that C divides D, because it has the same underlying set of irreducibles that could occur, P1 up through Pn, and the exponents are all smaller or less than or equal to in C than they are in D. Okay, so the details of this are a little bit murky because there's a lot of like rearranging factors that's going on. But the important thing is that any irreducible that divides C, there has to be some corresponding irreducible that divides A and irreducible that divides C. That same irreducible divides A and B. And the thing in C, they don't have to be the same irreducible, but they're associate. So just work one prime at a time and cancel one irreducible at a time. And each time you cancel, you're lowering the exponents by 1. So that's the big idea. But the takeaway is that in a in a UFD, you can compute GCDs of elements where you have prime factorizations just like you do in Z for integers that are given to you as a product of prime integers.